Good news for everyone who watched the last video. It looks like my brothers have done something in the past and I'm becoming more corporeal. So that is good news. We will still have a math professor next week, probably. So let's get into some probability finally. We've talked about a little of this stuff, and we'll talk about a little bit more here and then really dive in deep in the videos after this one. So we're just gonna kind of play with an example and introduce some terms with this example. So let's say that we have 10 jelly beans, and one of these jelly beans is blue, 2 of them are purple, 3 are green, and 4 of these jelly beans are red, which, yeah, it's kind of a bad outcome for my jelly bean taste, but whatever. So we have a sample size of 10. N equals 10, we might say. We're going to draw one jelly bean out of like a bag of 10. We're not going to cheat. I cursed it. Look at me go again right here. So experiment is our first term. And we've used this a little bit, but an experiment here in the context of probability talks about an attempt to produce a random phenomenon where we know what outcomes can happen, but not what values will happen. Okay, so in this case, an experiment could be just picking a jelly bean, looking at what color it is, and doing that 10 times, and then putting the jelly bean back. All right, so we know all the possible outcomes. All the possible outcomes are going to be 10 different colors of jelly beans. We just don't know what's going to happen, right? We do an experiment, and we, let's say we pick a jelly bean, look at color, replace, and we repeat this 10 times. That's our full experiment. Okay, so we know the possibilities. We're not going to be able to get 10 yellow jelly beans because there aren't any yellow jelly beans in here. Okay, jello beans? Did I say that? Jelly beans. That's our experiment here. So an event is a collection of outcomes. And usually we identify events so that we can attach probabilities to them. So in this experiment, each trial has a result, but the event is all of the outcomes. So if we're doing this 10 times, the event would be all the different combinations of colors that we can get. And since we're replacing all of these jelly beans, the number of total events here is huge. Okay. But this might be, one example of an event for this experiment could be 10 red jelly beans. Maybe every time we pick a jelly bean and put it back, it's always red. It's pretty unlikely that this is the case, but this is an example of an event. There are a lot of events here. The sample space is the collection of all the possible outcome values. The collection of values in the sample space has a probability of 1. So it's just all of the events, all of the outcomes. Okay, so the sample space is every possible outcome, right? This is just one. Whoa, that's quite the word. This is just one. The sample space is collecting everything. So this one up here just has a single probability. The sample space, if we combine every outcome, well, it's just like that relative frequency. When we add everything together for every possibility, that should add up to 100%. So if we want to find the probability of events, we do something called combinatorics, which sounds really fancy, but all combinatorics means is counting. Okay, that's all it means. There's an entire complicated field of math that just boils down to counting. And of course, it's still very hard and I can't do a lot of it. But that's basically what it means. We're going to count. So the probability, right? This right here means probability. That's what this P means of an event is just going to be, well, how many ways can this event happen? divide that by the total number of ways that anything can happen. Okay? So the probability is an event is a number between 0 and 1, right? It's often a percent. Right? 50% is 0.5. So 50% is still between 0 and 1, and it reports the likelihood. Like if I roll a die, the probability of a 6 is 1/6. The probability of an even number is 50% if I roll a 6-sided die. So there's a distinguishing thing here between theoretical probability and empirical probability. Okay, so theoretical probability is the theoretical one. It's what we're calculating. It's what should happen. Okay, what should happen. Whereas empirical is what did happen. Okay, so that's the big difference between theoretical and empirical probability. So if I roll a die, the chance of getting an even number is 1/2. But if I just roll 3 odds, then the empirical probability of an even number, an empirical probability based on that experiment, is that the chance of getting an even number is 0. It never happened. The empirical probability was 0. Even the theoretical probability was 1/2. So theoretical probability is what we use almost all the time when we can calculate it. But sometimes we have to rely on experiments and get empirical probability instead. And there's a lot of things that we can do so that hopefully the empirical probability is close to the theoretical probability. And one way to do that is to increase the sample size. So these other ones are going to pop up in future videos, but the law of large numbers basically just says that the more and more you do something, as long as they're repeated independent events and a couple other things happen, as long as everything behaves nicely, then in the long run, empirical probability will meet up with theoretical probability. As time goes on, as you do more and more experiments, empirical will start matching the theoretical. It'll get closer and closer and closer. We'll talk about the law of large numbers more later on in this class. And then disjoint is also known as mutually exclusive. This is the more common English phrase. Disjoint is the more common math phrase. Okay, this just means that two events cannot occur at the same time. So we can't get both an even and an odd number on a 6-sided die. We can't get a jelly bean that is both blue and purple. In our example, obviously, in real life, there are jelly beans that are both. But in our example, up above, these would be disjoint events. They are mutually exclusive. And the last thing is independence. The result of one event does not change the probability of the next event. Okay, so for example, if we draw a jelly bean and replace it after, then the next bean and shuffle it is independent. It's independent of the first one because we replaced it. But if we don't replace, then these are not independent, right? If I draw a jelly bean, right? If I draw a single jelly bean and I draw a blue jelly bean and I don't replace it, well, if I draw another jelly bean, it's really going to depend on what I drew as the first jelly bean. Because if the first one was blue, the second one can't be blue. But if the first one wasn't blue, the second one actually has a higher chance of being blue. So that if we replace, it's independent as long as we shuffle them. But if we don't replace, they're not going to be independent. We're going to use all of these terms in future videos. So it's good to be kind of familiar with them. Kind of a definition overload. So maybe just keep this in mind, come back to it when you need to, if you want a refresher on this. But that's kind of like an introductory, hey, here's a bunch of probability definitions. We're going to use them. Let me know if you have any questions, and good luck.